10.2, Example 4. In this example, we're going to look at how vectors can be used in real life to determine trajectories and determine the path that objects will take when affected by forces such as wind or water or some other pushing force on it. So before we dive into this word problem, the first thing I want to do is discuss a couple of terms and a couple of diagrams. The first thing I want to talk about is how to label north, east, south, and west. So this is north, east, south, and west. I remember it as never eat sour watermelons or never eat soggy waffles. Or a more recent trick that I learned is you kind of draw the US with the origin in the center. And this is the East Coast and this is the West Coast because that's where California is. Whatever you use, it's totally fine. So the next thing I want to talk about is east of north and north of east. So now let's just talk about it a little bit. If I want north of east, that is this way. This is north of east. If I want east of north, that's this direction. If I want this direction, that would be west of north. And this direction would be north of west. So using that same pattern, I'm going to go ahead and fill out the rest of this. And so now that we have this, this will help us when they give us bearings and they'll say it's 60 degrees north of east or 20 degrees south of west or things like that. All right, so we have a jet flying due east at 500 miles an hour in still air, which means we don't have any air resistance. And then the jet encounters a 70 mile an hour tailwind acting in the direction of 60 degrees north of east. The jet holds its direction heading due east, but because of the wind, acquires a new ground speed and direction. I want to know what is that ground speed and what is that direction. So the first thing I want to do is show you a little diagram. So here we go. I'm going to activate the plane and the wind all at once. The black line represents the original trajectory of the plane. The little blue arrow is my wind vector. So that's the wind pushing it. And then the orange represents the new path of the plane. So we'll watch that one more time. So the idea here is that if I were to take a still shot of this, this is what my vectors would look like. Now this should be over here at 500, but I couldn't screenshot at the right time. So the idea is as this plane is flying, the wind is pushing it, causing it to move up like this. Now how we actually solve for this is all you have to do is take this vector and just put it at the end of this vector. So like the previous examples, you just draw this vector over here, and then we're just adding vectors. So in order to find the components of the orange vector, we just need to do some vector addition. So let's first break down what everything is. Let's talk about my plane vector. My plane vector is moving 500 miles an hour east. So pretend this is north, east, south, and west. This vector has the component 500, 0, because it's on the x-axis. And 500 is the magnitude. My wind vector, however, is a little bit different. That is the blue vector right here. So in order to find this, I'm going to zoom in here and I'm going to go, okay, this has an angle of 60 degrees. So to find this component, it's going to be 70 because that's the speed, cosine of 60, comma, 70 sine of 60. So then my wind vector, 70 cosine of 60, 70 sine of 60. Now we're going to simplify that just a little bit to make our lives easier. Cosine of 60 is 1/2, and sine of 60 is √3/2. So then this is going to be 35, 35 √3. So that's my wind vector. Now, in order to find my brand new vector, the new path, I'll call that v, is just going to be the plane's vector plus the wind vector. So it's going to be 500, 0 plus 35, 35 radical 3. So this ends up being 535, 35 radical 3. And that is the component form of the new vector of the plane when being pushed by the wind. So now what we want to do is find the speed and direction. Well, speed is just equal to the magnitude. And to find the magnitude, we just do the square root of the components squared. And then when I end up working that out, I get that this is about 538.423. So that's going to be the speed of my plane. And now I want the direction. So my direction is going to be tangent theta is equal to y over x. So 35 radical 3 over 535. So then in your calculator, you go theta is equal to arc tan 35 radical 3 over 535. And you put that in your calculator, and it should spit out 6.464 if you're in degrees. So the new speed of the plane is 538.423 miles per hour, and it's headed 6.464 degrees north of east. And it makes sense that it's going faster because the wind is pushing it not only up, but also in the same direction it was going already. All right, now on your own, I want you to try this one. An airplane flying 20 degrees east of north at 325 miles per hour encounters a 40 mile per hour tailwind in the direction 40 degrees west of north. Find the new speed and direction. If you'd like a little hint on this problem, I'll just set up the directions for you. So if I want east of north by 20 degrees, that would be this. 20 degrees. And this is east of north. And 40 degrees west of north. So this is my wind. And this is my plane. So go ahead and give that a try right now. But before we do the simulation, let's actually set up each vector. So I'm going to do them separate. The first one I'm going to do is the plane. So I know that I need to be 20 degrees east of north. And so this is 20 degrees here, which means this number is 70 degrees. And that's going to come in handy because when we work with vectors, the angle is with the x-axis, and it's the smallest positive angle to the x-axis. So I'm just going to draw this vector here, and I'll say it goes to here. And it tells me the plane is moving at 325 miles an hour. So the magnitude here is 325. So in order to find the vector coordinates, it's going to be 325 cosine of 70 and 325 sine of 70. And that comes out to about 111.156, 305.4001. And it makes sense that the y is so much larger than the x. If we were to draw a triangle with this, we could see that the y value is much larger than the x value. Okay, so now we're going to go ahead and get the vector for the wind. And for this one, I want to be 40 degrees west of north. So this is 40 degrees here. But remember, the true angle that I want is going to be this one. So that'd be 130 degrees because I want it to go to the positive x-axis. And so to find this vector, I'm going to call it W for wind. Doesn't matter what you call it. And it's a 40 mile an hour wind. So it's going to be 40 cosine of 130 and 40 sine of 130. And I put that in my calculator, and I get about negative 25.711 and 30.641. And I know this kind of looks right because my cosine should be negative, sine should be positive, so I'm looking okay. So let's take a little look at the simulation and see what it actually looks like. So I'm going to reset this, and I'm going to press the button to fly, and I can see how much faster the plane is moving than the wind. And so what I'm going to do here is I'm going to draw this all on one plane back in my notes. The reason I'm taking time to draw this in is to show you that if you take this vector and add it here at the end of your original vector, you get your new vector. So if I take my plane vector and add it to my wind vector, I will get my new path. So when I add those together, I get 85.445 and 336.041. So now all I need to do is find the magnitude and the angle. So the magnitude is just the square root of 85.445 squared plus 336.041 squared. You put that in your calculator, and you get about 346.734. Now I need to find the angle, so theta is equal to tangent inverse of 336.041 over 85.445. And so I get theta comes out to about 75.733 degrees. So now I just need to write my summary because it was a word problem. So the plane is moving at 346.734 miles per hour at 75.733 degrees north of east. Another way you could write this is to substitute this bottom line and put 14.266 degrees east of north, because you can say it in either direction. Remember, if this is my angle, I can be 75 degrees this way, or I can be 14 degrees that way.